Okay, so as promised, proof of the fundamental theorem of calculus. Are you ready?
Yes.
Okay. So one of the nice things about proving this is kind of the strategy that we take for proving the fundamental theorem of calculus is a lot like what you would have to do when you apply integration to different problems. The strategy is pretty similar, so it's a good kind of introduction. Okay, so just kind of a few key things to kind of recognize. So we already talked about the fundamental theorem, but notice here, so capital F of x is any antiderivative, right, of little f of x. So here, for example, you can say that what is capital F prime of x? What would that be? That's little f of x, right? So that's what it means for capital F to be an antiderivative, right? Okay. All right. And then, so our interval, so we're going to start off by looking at our interval. So suppose you split up the interval a to b into n sub intervals. So just like what we did when we were when we split up the area underneath the curve into rectangles, right? And so we'll write it like this. So the subintervals are going to be from a to x1, and then from x1 to x2, x2 to x3, and then the last one would be x sub n minus 1 to b. And then you might maybe note a is our x sub 0 that we normally write down. And then what would b be? X sub b. B would be x sub x sub n, no? Right? This is the very last one, right? Okay, so this is simply how we split up the subintervals. So how many subintervals do I have here? N, right? So you can think of it kind of like the n rectangles, right? So those are the subintervals. And what's the width of these subintervals? Delta x, right? Okay. So when we did it, just to keep things simple, we made delta x be constant, but in reality, it can actually be different widths. So I'm going to put a little I in there. So, but it's not something that we need to worry about. Okay, now we have a theorem from way back, not that far. But I said that it was a very important theorem. It was the mean value theorem. So what can we say by the mean value theorem on every subinterval? Yes, so you've got the right idea. We just have to make it match up. So let me where would be a good spot to kind of put it? So okay, I'm going to write it and then I'm going to erase it because I'm going to need the space. But just to kind of refresh our memory, what is the mean value theorem? Remember, the mean value theorem says that so if it's continuous, on some interval, there exists some number c such that such that what? F prime of C equals to f of B minus f of A over B minus A. Okay, now this is the mean value theorem that we saw when we were just talking about it, specifically about the mean value theorem. Okay, so just what you want to do is don't get confused with the notation, but what we basically want to do is we want to apply the mean value theorem to every one of these subintervals. So we're not applying the mean value theorem one time, we're applying it n times to all of those. Does that make sense? Yes, you with me? Okay, so like for example, let me just kind of as an intermediate step here, I'm going to pick this one. So what would I be able to say with, because of the mean value theorem, just in that interval right there? What would I be able to say? So if I just apply the mean value theorem, which I wrote down right here, but to the interval from x1 to x2. So I need some f prime business, right? Okay, f prime of, so it's some number between x1 and x2, right? Okay, so we don't know what the number is, but that doesn't matter. We just know that there is some number, right? Okay, so I'm going to call it f prime of x1 star. Why star? Well, I don't know. Stars are magical, and and it's the magic number in there that we don't know what it is, right? Okay. All right, so there's some number between x1 and x2, which is x1 star, where little f prime of x sub 1 star is equal to what? F of x2 minus f of x1 over x2 minus x1. Okay, so we kind of want to just use this as a template. So we want to write down the general case, so this right here, notice, what is this? What is that? x2 minus x1. The difference of the x's. What's it? That's delta x, right? Okay. And then what else? What else? Okay. So now arg. I'm looking at this and I don't know if I'm going to have enough space. But okay, so do you guys see how okay, how about if we rewrite delta x over on this side? Is that okay? Instead of putting it on the denominator there? Yes? Is that okay? Okay. All right. So I'm going to erase it from down here. Okay. Let's see here. Okay. Let me. Well, it's good that I left a little space because actually, I'll write them out just to make it a little bit more clear. So let's see. What would the one before be? So not this one, but this one. So the very first one. If I do exactly the same thing, what would it be? F of, on the right side, I'm going to have f of x. Okay, f of x sub 1 minus f of a. Okay, good. And on the left side, I'll have delta x f prime of x 0 star, I guess. Okay. Let's see. Let's do... Well, no, I don't think we need to write another one. Okay, let's do dot, dot, dot. What's going to be the very last one? So on the right side, what will I have? F of b, right? Minus f of x sub n minus 1. Okay, and then on the left side, I'll have delta x f prime of xn minus 1 star, like that. So far, so good? Okay. So, do you guys notice anything interesting here?
Similar to the summation stuff we covered a few lectures ago, for one. In a general sense.
In a general sense, you're right. I just realized a small mistake. Are you guys ready to correct a small mistake? What is it? F of b be f of n. It is, yes. So you can use one or the other. I just chose to use f of b. But I actually, this is a little bit, it's not quite incorrect. It's just it won't lead us to where we want to go. Are you guys okay with me changing these little f's into big F's? And then what is the left side going to be then? So let me make this a little bit smaller. So we still have the delta x, right? Big F prime of x, yes, exactly. So notice here we're going to have big F prime of x and then whatever, right? X sub, but what is big F prime? That's a little f, right? Remember? So big F prime, so capital F is the antiderivative, right? So this is, so if I have little f of x sub 0, little f of x sub 1, and then the last one, little f of x sub n minus 1. Does that make sense? Okay. Yeah, sorry about that. I just went the wrong way there for a minute. Okay. All right. So now maybe you will notice. Okay. Do you guys notice anything interesting there? For example, what if you add up all of those? What do you get on the right side if you add up all of those? What do you notice about those two guys? It's just f of b minus f of a, right? Because see how all of the ones in the middle are going to cancel out? Meaning here there's an f of x sub 2. Here there's going to be a minus f of x sub 2. And then this f of x sub n minus 1 is going to cancel with the one before it, right? So the only thing left after all that is f of b, capital F of b minus capital F of a. Does that make sense? Okay, and then what about on the left side? What is that? If you add up all of those guys. So notice you have delta x, right, in all of them? And then what else do you have? F of x sub 0 plus f of x sub 1 plus f of x sub 2, 3, all the way up to n minus 1. So this is equal to the sum of f of x sub I from I equals, in this case, 0 to n minus 1, right? Does that look familiar? Sure does, right? because if I, for example, do, it would be much better if I had it backwards here, but it's too late now for that. If I do the limit as capital N goes to infinity, there's no n on the right side, so I don't need to put it there. But what is that right there? What is this? That is exactly equal to, what is that? The limit as n goes to infinity of the sum from 0 to n minus 1 of f of x sub I delta x. Isn't that exactly equal to the integral from a to b of f of x dx? Isn't that the definition of the integral? It is, right? And what is that integral equal to? It's equal to capital F of b minus capital F of a, where capital F is the antiderivative. And that's it. Does that make sense? So just with the mean value theorem, we proved the fundamental theorem of calculus. So like I said, this strategy of splitting up into, so notice here I have, I split this up into n pieces, right? N subintervals. And then I added them up, right? And then notice how I recognized, well, in this case I had to use the mean value theorem a little bit, but once I did that, I noticed that the sum that I end up, the infinite sum, is actually an integral. And then once you recognize it's an integral, then you can use the fundamental theorem of calculus to find that infinite sum. So it's pretty remarkable how you can have, like if you think about this problem, adding up an infinite number of infinitely small things, that is very difficult to do, right? But the idea that you can do, you can simplify that and turn it into a antiderivative and a difference, and then that's it. That's just crazy, right? I mean, yeah. What is it? Yeah, voodoo, yeah.
So when you were using the mean value theorem and you came up with delta x f prime of x n minus 1 equals f of b minus f of a, and you just took the antiderivative of all of the f's, including the f prime?
No, I just rewrote it. What it was is I accidentally used the wrong functions. So I applied the mean value theorem incorrectly in the beginning, is what happened.
So then where did the antiderivatives come from?
It's part of the assumptions, because so you have here in the theorem that you know that capital F of x is any antiderivative of little f. So you have that from before. So you already know capital F of x is an antiderivative of little f. So you're assuming you have that. So if capital F of x is an antiderivative and you apply the mean value theorem, this is the relationship you get. Does that make sense?
Honestly, no, but I'll read more into it.
Yeah, I mean, it's just a matter of, well, probably didn't help that I wrote it down wrong to start with. But if you just think about it, so let's say, so if you get rid of all the other stuff, okay, what do you know? I know capital F prime of x equals to little f of x, right? Okay, so just forget about everything else and you know that, right? Okay, then apply the mean value theorem to capital F of x on, say, x1 to x2, for example. So what is the mean value theorem? If you apply the mean value theorem to this function on that interval, what would you say? You would say that there's a point in there where the derivative of this function is equal to f of x2 minus f of x1 over x2 minus x1. Right? That's just the mean value theorem. The confusing part is probably that we apply the mean value theorem to little f of x, which is not what you want to do. And then it's just a matter of some small rearranging because, well, instead of doing capital F prime, just rewrite it as little f of x. And then instead of x2 minus x1, just rewrite it as delta x, right? Yeah. Jenna? It is. But it's the same as the difference between the endpoints of the subintervals. So it would come out to be the same thing. Although in this proof, we're assuming that the width of the rectangles could change. But it doesn't really matter. I mean, so the examples we did, they were all the same. Here we're assuming it could be different, but in the end it doesn't matter. Yeah, so because, for example, like let's just say hypothetically, so just to make sure we're on the same page here. So let's say, for example, you do, I don't know, let's see. What is that? Okay, that's 4 subintervals, yes? Mm-hmm. So this is 10 minus 0 divided by 4 is 2.5, right? So that's the width of the subintervals, right? But you can also get the width of the subinterval by subtracting, for example, here, if I subtract 7.5 minus 5, what do I get? 2.5. It's just the same thing, just looking at it differently than the way we looked at it when we were evaluating the sums as well. And then up here I have f of x2 minus f of x1, right? So if you take this and you just repeat it for all of those subintervals, then that's how you get what we had over here. That's how you get all these lines right here. And then if you add them all up, then you get the cancellation. All the ones in the middle cancel out. Is that a little bit better? So fun times, right? Any other questions about that? No? Okay, so why don't we do a couple more examples here then of applying the fundamental theorem. So we did quite a few last time, but can't hurt to do more. So integration is probably, no, not probably, the most important thing you need to learn in the class. For sure. For sure, for sure, for sure. Let's see. How about the integral? So last time we did some absolute value ones. Let's do this one here. So let's see. So the first thing is, remember, anytime we have an absolute value, we rewrite it as a piecewise function, right? So here, absolute value of x is either x when x is greater than 0 or minus x when x is less than 0, right? So that tells us where we're going to split up the integral. And so this integral, we're going to have, so let's see, so 2 plus absolute value of x is going to be the integral from minus 1 to 0, right? Because that's where we change functions, right? and then of some stuff, and then we're going to have the integral from 0 to 2. Does that make sense? Okay. So the only thing that's going to change is you're going to basically, you're going to replace the absolute value of x with whichever function is appropriate for that interval that you're on. Does that make sense? So like right here, for example, I'm still going to have the square root of 2 plus, but then I'm going to replace the absolute value of x with which one? With minus x, right? Why? Because that's what it's defined when x is less than 0. So here I'm going to have minus x, and I guess I should just do 2 minus x there. dx. And then in the other one, I'm going to have the square root of 2, and then in this time it's plus x. Does that make sense? And now we can integrate. So does the setup make sense for how you split it up? So it's completely based on the absolute value function itself. And all it is just a matter of rewriting the integral so that there are no more absolute values so that you can find the antiderivative. Yeah? So any questions with that? Or are we okay? All right. Now the antiderivative is a little bit tricky just because we haven't... so it won't be difficult once we do integration by substitution, which we'll do next week. But it's a little bit tricky because there's stuff inside the radical that's more than just x, right? So if this was just, for example, square root of x, then you would just use the power rule, right? So, well, can I use the power rule anyways? Kind of, sort of. So you can, yes, but you have to just be careful. So what's going to be the exponent here? 3/2, right? So I add 1, so 3/2, right? And then multiplied by 2/3. But just think of going backwards. If I get the derivative of this function, will I get the square root of 2 minus x? Not quite. What's missing? So if I were to test, so for example, if I test, get the derivative of 2/3 2 minus x to the 3/2, will I get the square root of 2 minus x? You won't, almost. So what is this going to be? This is going to be 2/3 times 3/2. 2 minus x to the 1/2, right? So far, so good. But then what do I have to do? The derivative of the inside, which is minus 1, right? So because this is a constant, I still can get the antiderivative. All I have to do is make this a negative. But it's only because this is a constant. If this was some variable or whatever, then I would not be able to do this at all. But you do have to be a little bit careful, right? Okay, so does that make sense? Yeah? So then this is going to be from minus 1 to 0. And then, let's see here, plus, what's the antiderivative of square root of 2 plus x? So it's going to be similar, right? 2 plus x, 3/2, 2/3. Do I need to do anything else with that one? No, right? Because when you get the derivative of that one, what is that going to be? That's just going to be that and then times 1, right? Which is not a big deal. So then this is okay. and this is going to be from 0 to 2. So any questions with that? Does that make sense? So a little bit tricky, right? All right, so now, what is this equal to? So let me erase this down here. All right, so let's see. So I'm going to have minus 2/3. If I plug in 0, I'm going to have 2 to the 3/2 minus 2/3. 2 minus minus 1 is 3 to the 3/2, right? Okay, plus 2/3, 4 to the 3/2, minus 2/3, 2 to the 3/2. Is that right? Nope. What did I always tell you? Be careful with your signs. There's a mistake in there. Where is it?
Shouldn't it be plus 2/3 in the first one?
Not the first one. The first one's correct.
Oh, no, the second one.
The second one,
First
right?
two are both the second.
Because it's minus the negative, right? So that should be a plus. Okay. All right, so just be really careful. All right, so then what is that equal to? Well, let's see. Can we combine these in a meaningful way here? So let's see. How about this guy right here and this guy right here? Those are like terms, right? So that's going to be minus 4/3 times 2 to the 3/2. Well, what is 2 to the 3/2? Well, I'll just leave it like that. Square root of 8 or 2√2, right? Yeah, I might as well, right? 2√2. No? Sound good? 2√2? Okay. And then, let's see. Well, I can't combine those guys, but I can reduce the 3 to the, so 3 to the 3/2, what is that going to be? What is that going to turn out to be? 2 √3, right? 2 square root of 3, because you subtract the exponents. So you end up with 2√3. Let's see. And then, how about that last one? So 4 to the 3/2, what is that? 8. Yep. Times 2 is 16, right? Okay. All right, you can combine these a little bit more if you want, but that's good enough. All right, so questions? Is that okay? Doing good?